linear Lipschitz sense. So it's basically the same thing that I've talked about at my presentation talk in the very beginning, but I will go right now in more details, probably a little bit faster, but at any point, if you have any kind of questions or I didn't make something clear, please be welcome to interrupt me and ask questions, or if I'm being too slow as well, let me know. So this is a bit of science about how to, one method to approach questions of the nature, how to study certain metric aspects of objects from homotopy theory. So when we have homotopy theory in topology, we just have everything continuous and don't think much about anything else regarding with metric, but it may be interesting to sometimes also know what does exactly the continuous mean, how much you need to stretch the space to map it. So that's answering a little bit of questions of that nature. So the setting that we have is we can have a metric space, and for a map between two metric spaces, we can define Lipschitz norm of that mapping as how much the distance is stretched. So pullback of a metric on y over a metric of x, or you can think of it as just the subnorm of the derivative of x. Basically everything you can think of as partially linear or even smooth, I think. So it's not much of quotation marks there, not much of a stretch to think of it that way. And when we turn our glance to more topological homotopy side, we can ask questions like, if we have a homotopy class of mapping from x to y, then what kind of representative for that mapping we can find, how small its norm can be. Or, for example, we want to extend a map, so we have pairs XA, YB, and we have a mapping on the subspaces. We know that it is extendable from topological point of view, and we want to see, say something about how well of an extension we can build, given that we start with a mapping that we know something about. And
are you mostly thinking about manifold X and Y?
Simplicial complexes are fine. Manifolds definitely yes. Like complete manifolds, yeah, but you should mostly think of it as simplicial complexes.
But kind of like for manifold, it's still kind of non-trivial results which you're going to discuss.
Yes. For example, the first example we will tackle, it's not non-trivial. So we will start with S3 to S2, and that is already posing difficult questions. So particular example of this kind of abstract situation is this more tractable setting where we have just two spheres, basic objects in topology. We have two mappings that we know are homotopic to each other, and say we know their Lipschitz constants. The question is, what can we say about the norm of homotopy between them? So we know they are homotopic. How short of a homotopy between them we can find? And as I also mentioned last time, you can phrase that question in a little bit more subtle and detailed way, because like here there's just some abstract nonsense. But when you talk about the homotopy, what you have is you have a mapping prescribed on the like x cross 1, x cross 0, and you want to extend it to the cylinder. And here you have different directions. You kind of have space-wise direction, time-wise direction. So you can you can separate the Lipschitz constant into a kind of a derivative in space direction, derivative in time direction. You can trade them in different ways. And sometimes you can get more by sacrificing the other. But since we have linear homotopies here, for us, we will just have this holy grail to build the homotopy that has just, so we hope for an answer like this, that it will be also a Lipschitz in time direction. And we won't bother with that kind of separation.
I'm sorry, what's a linear homotopy?
Yeah, I think I should put it the other way around. So it might be the case that you, for example, cannot build a homotopy that is exactly L Lipschitz, but say you can build a homotopy that is L squared Lipschitz. But it also can be the case that you can actually say something more that, for example, it is L Lipschitz in space direction and only L squared Lipschitz in time direction. So it is kind of the time required to go through L Lipschitz mappings is L squared. And so in that sense, we aim for the linear bound that we only need a linear time in terms of linear constants of the original map.
And so L Lipschitz means L is your Lipschitz constant?
Yeah. Any more questions? So the first kind of fundamental idea here, and also a convention for the subsequent illustrations that I want to introduce, is the following kind of set of correspondence. So we started with some mappings between the spaces, but as some wise people like Brouwer, Tom, and Pantragen realized, sometimes you want to think of maps in terms of the pre-images of regular values, and so you have this kind of picture of submanifolds, of frame submanifolds, but simplifying for now, that are a regular pre-image in your source. So for example, if I map this square onto two-dimensional sphere, kind of wrap it around, send all this dashed region to one point, and everything else is just kind of a polar projection of a globe, then I have this very regular value, the pole. Here I have my point, that is the submanifold that corresponds to this wrapping around. Or if I consider now a homotopy, well, here there's a constant homotopy of the same mapping. And the mapping is just that I collapse everything and do the same mapping, then the pre-image will be like that. And so again, I have this submanifold with a tubular neighborhood. So that is one way to look at it that is useful for visualization of what's going on. And another way is to look at this picture and kind of forget about all of the different things, I guess. So here we have a volume form that, a volume form that we can derive from the metric. And here we have this region filled by the pullback of that form. And so we can, again, relate to a mapping. How does it act on differential forms? And in particular, we can just, it will be useful to pick some specific differential forms of on Y that represent some homological or homotopical obstacles that we would need to overcome. For example, here we have this volume form that counts wrapping around the sphere. And so figuring out how they sit in X would give us information how the mapping look and guide us to build such mapping if we put together forms. So that's kind of there was not much of a statement here or a reasoning. It was just a kind of framework that will be useful for further considerations. Okay. And so I guess we can start with an example of, let's say I am trying to null homotope some map from S2 to S2. First of all, I can think of S2 as just a square that I identified by the boundary. It is just a bit of technicality to get to that case. And also, it is, again, a bit of technicality to shuffle the map a little bit so that it exactly looks like just a bunch of disks like this, where on each disk you either have a mapping of degree 1 or degree of mapping of degree -1. Just standard mapping so that here. And you want to null homotope that mapping. That is reasoning from the picture below, is to connect these kind of positive and negative disks with the tubes that cancel them out. And the first ways I will not be sure about the names of the people, but Larry Guth was also participant in doing that approach, was to exactly just take this combinatorial data of points sitting on a grid in, like you think of this as L by L grid, where on each tile you have plus, minus, or 0 degree assigned to it, and you want to build this whole connection construction. And that is the framework of how it was done the first time. You basically pick random heights of pillars over these things and just connect them with broken lines, and with good expectation they will not intersect, and you will get a linear homotopy from that.
This is not a one-to-one correspondence, right? There could just be like 1 plus and everything else could be minus.
Sorry, can you repeat the last thing?
It's not a one-to-one correspondence, right? Between the pluses and the minuses. Like
we originally we don't have any correspondence. We just know that some of them are positive degree, some of them are of negative degree. We just need to somehow cancel them out.
right.
We don't know that this plus should go exactly here, but it should go to some minus.
Okay.
So there is a way to spend time Okay, I wanted to go another way around. So I wanted to say that from this picture, I can already see that I should have time. I cannot hope to always have time better than a linear bound. And why is that? Because if I pick a plane here in the middle, I just span the whole left half side with positive degree, so that here I will have something like plus L squared. Here I have something like minus L squared. Then on this cross section, the degree should be equal to that degree because we transferred here. And so we know that L times T is at least L squared, so the time is at least linear. Should I go over it a little bit more?
Can you repeat?
Yeah. So we show that time should that this is the lowest bound that we can hope for, because if we consider a mapping that is all positive on left hand side, then the degree here would be, well, I guess will be that dimension L times this dimension L over 2. And we would have to have the same degree on this separating face, because that we have to carry all that degree from the left side to the right side. And the dimensions of this guy are L and our time t. So this thing has at least to be over to here. And actually, if you take this argument and can just go backwards, starting from the degrees, you can actually get another more algebraic and more useful, theoretically speaking, way to prove, to construct an extension in linear time. So we can consider how our volume form changes in time when we go from the bottom to the top. So we have some form that I will call alpha. And so ideally, I want somehow just dissipate that alpha. And when I extend it, or if I take the image of the same form on the whole space of the homotopy, I would want it to be something like 1 minus t alpha, and it just decreases linearly over time. But of course, it cannot just vanish without a trace. It has to move somehow. And you can express that in a way that if you take d of that, you will have something non-zero, but the initial form is closed, so it should be 0. So we have to add something, and we can say that, okay, this alpha, we know that the initial mapping is null homotopic, so there is as much pluses as there are minuses. So there is one form beta that d beta gives us alpha. That is kind of just drawing the connections of pluses and minuses just plane on the square. And we can just say, okay, let's add this guy here, and then that would be a closed form. And what that means is that we, roughly speaking, have assigned to each square in this picture a degree, so that on any cube, the total degree vanishes, so we can extend the mapping inside of the cube. It is kind of an abstraction theory where you have some form, you want to get rid of it, you find the primitive of that form, and you apply it on the lower cell times t to put degree there, so that after all you get nothing in the end. Okay, that might be a little bit of a tricky place, so I probably should stop here for questions.
Excuse me, you're working with surfaces, right?
Right now, it is just purely two-dimensional surface to surface, but the next comment that I wanted to make is that you can just do exactly the same thing for SN to SN. So in particular, that argument is that case, and even if we have here something like that, or then that also works. And the reason is that what are the homotopy groups? What are the classes of mappings between spheres? Well, we have this first non-trivial invariant, the degree of how equidimensional spheres are around each other, and we have dealt with that. But also there are higher homotopy groups, but they are mostly finite. And the fact that they are finite is very convenient, because they cannot stack up on each other, so you have then some bulky weight that you have to carry around, so to say. They only can occupy so much space. So if we are walking kind of up to a constant whatever, we can just ignore them for most of the part, and only deal with invariants that are non-zero rationally. So the degree or Hopf invariant that can appear in the case where target is even dimensional and the sphere is of dimension 10 minus 1. And that is something that we will tackle next. So, one might say, well, one thing that I forgot to mention is that, so where here comes the fact that, like, how do we get actually quantitative bounds from there? Well, we have to make sure that all our forms are, they have the same bound, that beta is a nice primitive form to alpha, and it is some isoperimetric lemma that is just a little bit of technicality, that you don't kind of connect all your stuff through a bottleneck, you kind of spread it, all your connections evenly.
I'm sorry, could you explain, could you repeat that? Right? What is this thing about bottlenecks?
So in this case, if I have a bunch of positive degrees here, a bunch of negative degrees here, if I had picked my beta so that it would be supported just on a single phase, then through that phase would have to go all the L squared degree that I had to transfer. And that would be bad because then I would have to spend not linear time, but L squared time, or even worse in higher dimensions. So I kind of have to make sure that at any point beta is bounded and doesn't go through bottleneck in that sense.
Yeah, thanks.
Okay, and so you might ask, well, why does not this same argument go for Hopf invariant as well? What is different in that regard? And the reason is that while the degree is just counted by taking the preimage of the form and integrating it, it is kind of the same degree as you expected from the homology. The Hopf invariant behaves a bit differently. For example, you can pack much more of it than you have volume to operate with. So what I mean is that, well, how you compute Hopf invariant, you can say that, okay, I take my S3, I take my alpha, take some primitive form beta and integrate it, or equivalently saying that I integrate over for ball that S3 bounds of and so here comes the funny thing is that we see it on S3 that is three-dimensional, but we integrate this four-dimensional form to get our invariant. So inside of the volume of L cube, we get the invariant L, well, we may get invariant L to the fourth. So in particular, okay, I just erased it, so I wouldn't refer to it. So let me just fix it. Yeah.
I probably just missed this, but is alpha a two form on S3 or on the four ball?
So I put here like we take an extension to the four.
Okay, so you get some kind of extension.
Yeah.
And does it matter what the extension is, or I suppose it doesn't for what you're.
So here I am doing this mostly for the sake of putting a validation to that statement. I will also just give you an example of how that works out. So I don't want to get far into it. And this is just kind of the Stokes formula. You can integrate D over whole thing or integrate the thing over D. And so why is the fact that we can pack a bunch of Hopf invariant into small places bad? Well, because if we have a bunch of Hopf invariant here, it might take more time to transfer all of it through the same boundary. So if I just try to replicate the same schema literally, so I'll say have here some mapping of degree all to the 4 here, all to the 4, and I try to have here my tiny grid, and I want to transfer all of that invariant by putting tiny little Hopf invariants in each of these cells. Then I would need L to the 4 of those cells. And so given that this thing is L squared, I will have to have time at least, again, L squared. So that's not very good, but it is some result. It is one of the earlier results, and you can also put it in a more rigorous form of taking forms, taking primitive of those forms, and use them to guide you to build the actual mapping, knowing that they signify the degree of the mappings that you want to put there. But clearly that is not the most optimal thing that we can hope for. And indeed, at least if I knew that I just had here this mapping of huge degree, I definitely could transfer it to the other side in just linear time if I just take a mapping that looks like just the same mapping on all such sheets, or I can even just say that I can transfer it from one side to another by just composing it with the change of variables that makes. The point that I wanted to make with this is, since if we hope to operate on tightly packed invariant, then we have to take that whole big mess and carry it around as a whole. And you can take that intuition and put it into an actual argument that goes something like follows. So this approach suffered from being too homogeneous. We wanted to kind of micromanage everything by infinitesimal adjustments, I guess. But we have to operate in a little bit more crude fashion, which is, so let's have this space. So this would be my S3. This is time. And I subdivide everything in this fractal way. So that on the very bottom, I have maybe very complicated mapping that I start from. On the very top, I want to get something very simple that doesn't present any issue. And I want to get from one to another. And the point is to break up this complexity into kind of hierarchical organization, so that, for example, if I have here something closer to my L to the 4, and here something closer to minus L to the 4th, then what I do on the very top, I say, okay, there are some little corrections that you will bother with lately on your own. And here I just know that I have to transfer that big chunk from here over there. So I just say, okay, here I will put exactly Hopf invariant of degree L to the 4. I can just pick a mapping with this high degree and hope that from their own it will be untangled later in an iterative fashion, and any excess that I have transferred will be kind of reshuffled later on more fine stages. And that is all kind of a good idea on paper, but the reason that it works is that these tight mappings are in a way simple so that we can actually treat them as just unit mapping with a different scale. And what I mean by that is that so we kind of have this dichotomy between lots of tiny Hopf links and that picture corresponds to a situation where we have our S3, we have our standard of mapping with degree 1, and how we get this population is that we just compose here with a mapping of degree L to the 3, and that's why we get here not as much of a degree. We have scaling on the left side, and it is just L to the 3. But on the other hand, what we can do is we can just, instead of this bunch of tiny loops, we can get a huge bundle of interlinked cables that correspond to the situation where we have scaling on a different side, where mapping is being post-composed with mapping from S2 to S2, rather than pre-composed with a mapping from S3 to S2. So here, kind of the whole space is subdivided to little cells where tiny mappings are, but here there's just one huge cell, but it is composed of mappings that are all of tiny degree plus mappings there. And the point is that whenever I build these constructions, I approach this fixture from the source space. And so I can forget temporarily about this scaling mapping and just operate with it as unit big chunk, so that for each subsequent scale, I will have all the time a picture of bounded complexity. So I wanted to kind of balance out Haif waving and delivering the intuition and actually delivering the construction. So there probably are a lot of questions.
Can you explain why there's a difference between L3 there and L2 there?
Sorry?
Why is it L3 and then Hopf versus Hopf and then L2? Shouldn't it be L3 again on the other side?
So when we have mappings from Sn to Sn, then we can put their degree of L to the power of dimension of that sphere. So that's why here we can put L3 and here we can put L squared, and this way we kind of have this alpha of norm L squared, and when we integrate it square, we get the degree of L to the 4.
I see. Okay.
Or you can say that it's kind of in the picture of these manifold preimages, you have L squared circles like this, linked with L squared circles like that. L squared times L squared is 2 to 4. All right. So this is the, I guess, second main idea is that the essential feature that uses this kind of iterative argument is that we have on the target these kind of self maps that scale it nicely. So let me write that down somewhere. So we started with the question of whether there are homotopies that are linear in time. And we can get there using that scheme from a essential property that we used from S2. So if there are maps of X to itself that are Lipschitz, and they act on HI by let's say that they are here approximately on Lipschitz, and here they act exactly by multiplication by the degree that you expect them to act. So this property is the origin of the definition X is scalable. Starting from here, we can get these linear homotopies, but actually if we know this linear homotopy property, we can actually also get these scaling mappings arguing by degree, because when we want to extend a mapping to an X cell, we have a mapping on its boundary, and we want to extend it to the disk, so to null homotopy it without ruining the Lipschitz degree. And that is exactly what is provided by that the first thing is saying. And that is all neat, but the usefulness and the significance of this observation that Fedemanin noticed was that that property is actually, you can relate to a different thing. So if you take so given you have a closed form on X, you can get to a homology class, and you may hope to have a lift back to closed form. So you can maybe present cohomology of X by some actual differential forms on X, so that even the structure of the algebra is preserved. And this thing is, on one hand, is something that is sometimes either easy to construct or to disprove, this kind of property. And it is tightly related to the previous property. So these two are actually also equivalent, with a little asterisk all over here. Every spaces are supposed to be formal. That is a little weakening of this assumption. That is I want to get into, but you present as forms more lucent object rather than cohomology. And so where does this correspondence come from? Well, if you just take these self-mappings that scale X more and more and go to a limit, if you have a good bound on the Lipschitz constant, then then you can look at the pullbacks of these forms, and they will be, if you scale them back down, uniformly bounded, and you can pass to a limit point and get some forms on X that will present a cohomology and will give you correct, well, yeah, probably not have much time. So I'll just say that you can build this map by just taking a limit of these pullbacks scaled back to, well, scaled back by the L to the I. And
I find this a little strange because closed forms are like homotopy classes of X into Sn, right? Like they're pullbacks of that. But here you're thinking about the maps from Sn into X. Like I guess cohomology is whatever homotopy classes of maps from X into, oh no, that's only true in dimension 1. I mean, I don't think this comment has any context, but I was wondering.
There is like Sn here serves as a substitute for whenever you are arguing by iteration by skeleton, and that can kind of happen on the both sides. So if there is a conflict, it is probably resolved in that place where it is just. Yeah, I'm just kind of talked myself into a little bit of a meditative state, but I would have to think a little bit.
I'm also a bit confused. Maybe it's related to that. I mean, you can have some space X, which is very complicated in homotopy, but its homology is like could be trivial, right?
Yes.
But you're saying that like, so X could automatically be scalable, but then you're able to relate homotopies, which a priori are much more complicated. I don't quite understand.
So the let me go on a limb a little bit here and say that the fact that you can represent that cohomology in this situation kind of encapsulates the fact that you don't have a homotopy that is very uncontrollable, because it would pop up in having to the fact that you can present this cohomology kind of says that it is actually not that much more difficult than you don't have homotopy issues that you cannot address like that Hop situation. Because here we're not operating with I just wanted to first probably finish the talk and then try to answer questions, because at this point I'm looking at. So my claim was that given scaling, self-scaling mappings, you can get by taking a limit a representation of cohomology, and given a representation of cohomology, you can get back self-mappings that are scalable, because you can just take that representation and it does tell you how much of a degree you want to have on some small simplices. You just have to integrate a corresponding form across that simplex. And the fact that it preserves all that the forms are closed and that the products are preserved makes sure that it actually patches up and no higher homotopy issues arise. And just to briefly give an example of how that works. So if, for example, you had in algebra so elements in degree 2, so that they have non-degenerate pairing to a single element in degree 4. And you want, so this, for example, can happen if you take a few complex projective planes and take their connected sums. Each CP2 gives you an, what am I saying? Yeah, each CP2 gives you a two-dimensional element, and square of each of them is just top-dimensional class. But when can you present this algebra in the forms on X? Well, you can ask this question even whether you can present it in just forms at one particular tangent space. Then its second degree bilinear pairing there has a signature. Oh, yeah, it's just. Yeah, it is 3. So I can fit there up to 3 generators, but no more. And that means that connected sums of CP2 are scalable for up to 3 copies of them, but starting from 4, they are not. And you can find straightforwardly homotopy classes that do not have linear Lipschitz homotopies there. And that was actually what led to discover that, because I was explaining on these noodle pictures to Feria that, well, I can even build up constructions of the same thing going on for connected sums of CP2 when there are at most 3 of them, because I can put the degrees like here, like that, and like this, like the Bernoulli flows from the hydrodynamic talks, or they were where you have a bunch of different lines on intersecting. But if there are more than 4 of them, then I don't know what to do with them. And he realized that I actually was representing differential forms that have 0 product with each other. And that's how we got there. And for example, if you here instead of 2, you have 8 and 16, and you take Newtonian projective plane, then you will have this huge number of 6, 4, 3, 5 or something. That up to that number, you can put all the noodles in different directions so that they don't intersect each other, and that machinery works. But up to that point it works, but if you want to put more of them, then they no longer fit and the space becomes non-scalable. Okay, I think I'm exactly where to be. So I guess I can try again to answer questions if there are still something that I could probably answer. Thank you. Questions?
So, like, if it's, are there any like theorems that say that you can't do it with linear, with L in time, but you need L square?
You can construct examples where you need some ridiculous degrees by taking kind of links of links of links, etc. But if you confine yourself to the technical assumptions that we work here, then there is this method that you can say, well, if you even cannot represent the homology in the differential points at one point, it is something that it is rather straight, like algorithmically you can check it. If they do not represent, then you do not have linear homotopies.
Oh, that's a theorem. You
Yes.
cannot represent it.
Yes.
Oh, I see.
And the current suspicion is that you only need some log factor there to add, because you can kind of resolve the issues that come up by kind of spreading all these blocks a little bit to reach the middle with a little tube that that's the thing you wanted to do. But yeah, knowing that will tell you that you cannot have linear homotopies. We don't know yet if there are examples where you can represent at one point, but you cannot do it overall, because that is kind of much more not the clear thing. It is infinite dimensional space, kind of difficult to analyze, but that definitely gives you bound from a different side. Yeah, I mean, the point is that you have both directions here of implication. So if you have linear homotopies, then you have representation.
Thanks.
Other questions? Well, if not, I guess we can enjoy the tea.